KeShawn, thanks so much for taking the time to join us on Astrolennial today.
Of course.
Um, yeah, I was really impressed. I found your profile on Twitter when adding a bunch of folks from the astrophysics world, and your profile definitely stood out for a variety of reasons. And I'll let you introduce yourself to the world first.
Okay, cool. My name is KeShawn Ivory. I'm an current grad student. I'm a master's student at Fisk University in physics, but my specialty is astrophysics. So I'm in a program called the Fisk-Vanderbilt Bridge. I'll get into what that means a little bit later, but basically just know I'm a grad student. I do astrophysics. For undergrad, I went to Rice in Houston. I'm originally from Texas. And yeah, that's what I do. Other stuff about me, I sing. I was in an acapella group all 4 years of undergrad, and before that, I was in choirs since like literally the fourth grade. So that's a huge part of my life and always has been. And yeah, that's a pretty brief and basic introduction to me.
Cool. No, that's a really great introduction. So, music's clearly an important part of your life. And then in undergrad, you didn't just major in astrophysics, you also majored in French.
Right, yeah, I doubled in astrophysics and French studies. That's true, because I've taken French since I was like 12, because in middle
Mhm.
school I needed a second language for like state, requirements. And Spanish in Texas seemed really ubiquitous, so I wanted something that felt a little bit different. So I picked French, and then I just stuck with it because I needed a language to like take exams in when I got
Mhm.
to high school. So I just stuck with it, and then I didn't want to forget it, so I picked
Cool.
up the major when I was in college.
And have you, is it something that do you continue to read French books?
Yeah, I do. I continue to read French books. My phone and my Google Chrome are both like set in French. So
Oh
every
wow.
time
So you're really invested.
every time I pick up my any kind of technology, like websites load in French. Like because Google Chrome is set in French, like all the
Mhm.
articles that it recommends me, like current news articles and stuff, they're French language articles. So it'll be stuff that is happening in Europe, and I'm like, oh, okay, cool. I get to stay up on kind of like world news, which is really cool.
Yeah, that's great. And you get the perspective of not having to have French or European news filtered from the American perspective, which I bet
Exactly.
has some pretty key differences.
Exactly. And conversely, seeing American news filtered through a European perspective,
Hmm.
which is very interesting for sure.
Yeah. Is there anything that stands out, like big, like any forms of censorship? I feel like when I went abroad before, I would see pictures in foreign newspapers that show like the effects of violence versus
For
while
sure.
watching
For
something. Is
sure.
that the case still?
It feels like when I read, for example, like Le Monde, which is a French publication,
Hmm.
it feels like I don't know. I don't want to say like more honest reporting, but kind of more straightforward reporting. Like we're going to
Mm,
cover this thing, and we're going to cover it from top to bottom, and we're going to give you all the details. And I feel like that happens whether it's something that's happening in France, whether it's something that's happening in the U.S. I feel like they
mm,
cover everything with the same kind of like integrity, which I feel like U.S. media kind of does a bad job at keeping things consistent in terms of
sure.
like prioritizing what they cover and how they cover it.
Mm. Yeah, that's really interesting to think about the lens with which our media reports stuff and why that's the case. But going back a little bit to your earlier career, so you were singing from an early age. You were studying
Hmm.
French because you had to, but clearly you love it.
Yeah,
Where did the passion for STEM come from? Because now you're
right.
an astrophysicist, and I think maybe something worth mentioning that I want to hear more on is eventually you want to become a planetarium director.
Yes. So where did that passion come from? It's kind of funny. When I was like eight something, my English teacher, Mrs. Mann, she assigned us like one of those awful like lexical activities where you have to look up the word in the dictionary and write down the part of speech and write down the whole definition. And I dreaded them so much. And so one of the words was astronomy.
Mm,
And I kind of roundabout knew what that was. I didn't really know what that was, so I, looked it up like I had to. And as I was writing the definition, I was like, this actually sounds pretty cool, like space and celestial bodies, stars and planets, and all that stuff. So I kind of kept that in the back of my mind, right? And then my grandma, she had these World Book encyclopedias that were from like 1988 or something. So they weren't like super current, but I just loved reading them as a kid. I would literally pick them off the shelf, and I liked to read articles about like U.S. states. I don't know why. I just read like all 50 states. I was so obsessed. Memorized the capitals, points of interest, and everything. And so I picked up the A volume, and I read like astronomer, because I'm like, okay, if that's what I want to do, I should probably know a little bit about that career. I guess even as like an 8-year-old, I was kind of pragmatic. Like, what does that actually entail? So I opened up the book, and basically it said they kind of sit at computers and just like process data, which is true. I know that now. And I was like, okay, that sounds like a cool job. Just look at space stuff every so often. You might go to a telescope and actually get the data, and then you spend the rest of the time just analyzing it with some coffee in your hand. Like, that sounds pretty awesome. So when people asked, like, what do you want to be? I started saying that, like, astronomer. And over time, it kind of shifted to, like, astrophysicist, which is, like, basically the same thing, but, like, a little bit more specific. And, I mean, I just never really changed. Like, it came time to go to college. I had to pick a major. So I was like, oh, well, astrophysics. Like, what else would I do? So it's always just been, I guess it started when I was 8. And it just never changed. Never changed.
Oh.
But like you mentioned, it was never my only interest, because I sang and I did French, and I've always liked a number of things.
Yeah, I mean, it's so interesting. And I wonder, when I was chatting with Moya, we spoke about exposing people outside of the astro discipline to astro concepts, and how a lot of times taking different frameworks or different perspectives and applying it to astro reveals things that maybe somebody who otherwise would have had like a pure STEM focus, maybe they wouldn't make the same discoveries or have the same epiphanies.
Right. And you mentioned a little while back, like planetarium directing, and now you mentioned like bringing astro to like people that don't necessarily know the concepts. I think that those things are kind of at the crux of what scientists do, is like communicating the work that we're doing to the general public. Because I mean, if you just, in a very pragmatic and practical kind of sense, if taxpayer money is funding a lot of grants, then the people that pay taxes should kind of know what we're doing and what's going on, and feel like they're being served by what they're paying for, what we're paying for. I guess I pay taxes too, but and in the future I want to direct a planetarium, and so I arrived at that conclusion. It was not immediate by any means. For a long time, I thought I was just going to go down the academia path like everybody else, and I was going to be a professor. I was just going to go, get my PhD and then do some kind of postdoc and then some kind of like, junior position, and then move on to some tenure track thing, and that's going to be my life. But like in 2017, I was doing a research internship. I was at Harvard for a summer, and I was having a lot of fun. I was, but I looked around the room during a group meeting, and I was like, I looked at my PI, and I was like, if I wake up like 30 years from now, and I'm sitting in, my PI's chair, I'm sitting in the professor's chair doing what he's doing, I don't know that I would be happy. I don't know that that's the kind of life that I really want for myself in the long term. So that was really concerning for me, because it's kind of all I had ever wanted, and suddenly I was realizing I maybe don't want it. So I had to do a lot of thinking about what I actually do want. So I had to get back to the roots of why I even like astronomy. And so back at Rice, I was a TA for the non-majors astronomy course, and I loved it. I loved getting to have an office hour, getting to talk to people who weren't so heavily invested in this. It wasn't their major. It was just something they were taking for, distribution. They had to take a science class, and so they did. And I loved it. I love getting to communicate concepts to people who don't feel like it's like, life or death, make or break, just getting to talk about it because it's cool. I thought about that. I thought about a trip I took to a planetarium when I was a kid and how cool I thought that was. And I was like, hey, wait, maybe that's what I want to do. Because I realized that as much as I like doing research, I even more like talking about my research. So I was like, okay, I have to do something with like an outreach component, an education component. I have to reach people. And so then I got to thinking about what can I do in that capacity, but like with a PhD, what like super specialized training, what kind of job could I get that still has me talking to people? And then I did some like light reading, and planetarium director popped up because a lot of the time they want you to have a PhD because you're the person that's got to stay up on the literature. You're the person that's got to make the calls on, what astrophysical discoveries are we going to make planetarium shows about. You're the one who's got to make the calls on like who are we inviting in for lectures. I mean, there's a great amount of expertise, and you hear people say like you have to really be an expert in a field to explain it to non-experts, and that's exactly what this is. Like getting a PhD is necessary for the kind of work that I want to do because we're talking about like little kids, 8-year-olds, and I have to break down current discoveries in astrophysics for like second graders. So I'm pretty excited now that I know I have a clear picture of what we want to do. And so my friends, Ashley Walker and Elizabeth Gutierrez, they're fellow astronomers of mine, young, astronomers of color. They did that internship at Harvard with me that year. And we decided as a group that we really would love to, in the future, when we're in a position to do this, found a planetarium. We're calling it like the People of Color Planetarium, a planetarium that's directed at centering the narratives of people of color and also all the intersections, right? Like women and queer people and disabled people and all those intersections with people of color, because basically we want to really expand people's notion of what scientists can look like, what astronomy can look like. It's not just, Einstein and Ehrenfest and Schrödinger and Eddington and all these other white men that I could just name for hours. There's more than that, especially now it's growing, and we really want to showcase that. So that's like a very long-term project that we are.
I'm really glad you covered that because that was going to be my next question. It's not just about becoming a planetarium director, right? Because you said, sure, you have to get the credentials, you have to become the expert. And then it's about the approach. It's not just building a diorama, right? I mean, that's oversimplifying it, but it's also how do you communicate the message and what message are you communicating? Because science, it's about the facts, but I mean, so much of how science is done depends on ethics and inclusivity. And so many different types of people contribute to it, but those people don't get the recognition that they deserve.
Absolutely. And you know what? The thing about science and ethics, I was just in a tweet thread, we were just talking about this kind of thing. Somebody, they replied to a tweet that I said so my friend, she had said, STEM majors, aren't smarter than other majors. It's just a different major. There's no need to like compare types of knowledge or types of intellect. And I retweeted that. I was like, that's so true. And, I majored in STEM and humanities as well. So if you ever try to, come to me to mock humanities or any other kind of major, I will remind you that I majored in humanities and I did way more like deep thinking in my French literature classes than I ever did in my astrophysics classes. And someone replied to that with this great comment. They said, the lack of humanities education for a lot of STEM people is exactly why we're struggling with ethics issues in STEM right now. And I was like, that's such a great point. Oh my God, that's such a great point. And
very well put.
So you bring that up that, a lot of science is based in ethics, and that's super concerning because a lot of scientists don't get the kind of training they should in ethics and things like that. I took a course in social science when I was an undergrad. It was like an archaeology course. And a large part of what we did was museum studies. So we went to a museum, we talked about the layout, and most importantly, we talked about how it was not objective. The way the museum was laid out was done with a goal in mind. The people who curate these things lay out the museum in a particular way to, just like you said, communicate a very particular message, and it's all very arbitrary, and it's all very intentional. And I think that STEM is missing that. STEM is really missing that sense of like understanding that what we do is not objective. We love to believe that because it's the natural world, that it's completely separate from human influence. But that's just not possible when humans are the ones doing the science,
Right. And the ones that are doing the conquesting, so to speak, are the ones that get to write the history. So
exactly.
Yeah. And it's so I was having a conversation about this with friends earlier too, and let me see if I can verbalize it effectively. But basically the thought is, and the museum might be like a good physical representation of that, of take a frame of society and then, maybe look at the museums, scientific museums, whatever, and look at them as sort of as a representation of us as humans saying we have some level of intellectual superiority. Like we figured it out. Certainly make the argument that technological advancement in science has come leaps and bounds beyond what we've been able to discover in, say, the 1500s. But go
Right.
back to the 1500s and imagine the level of science they had there. I would imagine that relative to them looking at themselves back towards another 500 years, they probably felt like we have the answers, right? And maybe there was more religion mixed into justifying that. And now we're at a
Right.
stage today where we're saying like we know so much, like science is in some ways like this infallible thing, but this is, I guess my question to you would be like, and my theory is that it's impossible to guess this, but say that science, that all collection of all facts in the universe equal 100%. Sometimes it feels like the nature of science today, we feel like we've gotten, I don't know, we say that we've gotten like 50% or 60% of the way there, that we understand the laws of nature, that we understand a lot about our universe, and like every additional discovery is incremental, that there aren't many paradigm shifts left relative to what we had before. My argument is that what's to say that we're even like 1% of the way there, right?
Right.
Or if it's even possible, or if this is just like a perpetual discipline where there's unlimited discovery.
Right. It's funny. I feel like everything everything reminds me of a tweet somewhere along the line, but this does remind me of a tweet. A good friend of mine, Tia Martineau, she's a physics grad student as well at New Hampshire. She tweeted, essentially, she was saying, does it ever stress y'all out that physics is kind of like a best guess? It's just one possible model, and we put a lot of stock into it. We take a lot of time to flesh it out, and it could all just be wrong. And I was like, well, no, it doesn't really stress me out because I don't think that we can ever really know anything about anything for sure, and that doesn't upset me. That doesn't stress me out. I think that's kind of the nature of how things go, and that's not necessarily a bad thing. But if you feel that a life spent, investigating an issue, whether all the conclusions you come to are true or false in the grand scheme, the point is you put time and you put energy into figuring out something, and whether that something is right or something is wrong, we've learned. If it's wrong, we've learned that it's wrong. If it's right, we've learned that it's right. And so we had paradigm shifts, like moving from Newtonian gravity into like sort of like Einstein general relativity. Like we've had these paradigm shifts before where we build on things. So we realized that maybe certain things only worked in certain regimes.
And can you actually sorry to cut you off. Can you take a moment so a lot of the audience isn't even going to know that shift took place. Like pretend we're a planetarium audience for a second.
Yeah, of course. Great practice. Awesome. Sure thing. So, a while ago, a couple hundred years ago, we didn't really have, before the 1900s, before the 20th century, we didn't really have our sense of like what we call sort of modern physics, or like our modern approaches to gravity. Because gravity, what goes up comes down. Something with mass attracts other things with mass, and only works in one direction. Well, Isaac Newton's idea is that very classical idea. You hear the story about like he saw the apple and it fell, and he was like, why is that? That's a very classical notion of gravity. It's simply something with mass attracts other things with mass, and that force is proportional to, like the inverse of the distance, or like the inverse square. But basically, the farther away something is, like the lower the gravitational attraction is, or the less massive something is, the lower gravitational attraction. Classical idea, and it explains most things, like day to day, just like everyday quotidian stuff that occurs, like the literally drop something and it falls, like that explains that beautifully. Earth is a big thing, so big mass means that it's got large gravitational field, so anything in that field that's even reasonably close to the center, and by that I even mean like on the surface, is gonna fall. 9.8 meters per second squared. That's the acceleration rate for things on the surface. Well, in the 20th century, in the early 20th century, Einstein found out that didn't necessarily apply like in all regimes, because if you got to things that are massive enough or dense enough, you could see this warping of, so it's going to sound kind of wild, but like space-time, right? So you could think of like space is three-dimensional. So you have a length and a width and a depth, and that we're all used to, right? But you can think of time as almost like a fourth dimension, right?
Mm.
It's another thing that can vary, which is an idea that we didn't have, again, before the 20th century. But so 4 dimensions, sort of your length, width, depth, time, and that works around very massive things. And the reason why we don't notice it in our day-to-day lives so much is because we just don't work with things that are that massive. We just don't. Like, the sandwich that you have for lunch is not that massive. Like, we don't see things that are that big. But I'm talking about things like black holes,
Mm-hmm.
very far away, very unfathomably massive things. That's when we see this general relativity, this warping of space-time. So light bends, literally, it bends around these things. And the important thing to note about general relativity that's so wild is that it's not that light is taking a non-straight path. It's that space-time itself is warping in the presence of this gravitational field, and light is just following a straight line in a curved space, which, like, when I learned about that, it blew my mind. Light is just following a straight line, but space itself is curved, because light always goes in straight lines, but space itself is curved, which, oh my God. So that's the paradigm shift that happened. And things like that occur, and they don't scare me. They don't scare me, because it just means that we're either getting closer to the truth or we're getting closer to finding out that it's all a lie. Either way, we learn something. You know what I mean? Like, it's not pointless. It's never pointless.
I sort of want to run a ridiculous theory past you and see what you think about it. How scientifically improbable or illogical it is. But when I was chatting with Moya, one of the things she ended on was a fun fact about different theories about how the universe ends. And I guess one of those theories is the universe is perpetually expanding, and at some point there's, I guess, a rubber band effect, and then everything starts snapping back into place, goes into this singular point, and then the Big Bang happens again, or whatever it is that results in the universe happening the way it does. Now, the way I perceive that is I'm going to use non-technical terms, but when the universe explodes from that singular point, I guess the outward trajectory of all the different particles, like, yes, it's unimaginably complicated, but there is maybe like a mathematical pattern, right? And say the concept of time, time makes us feel comfortable with our mortality, but in reality, everything is just infinite. It just is. And that this process, if it exists, happens perpetually. It's happened infinite number of times before this reality, and will happen an infinite number of times after this reality. What's the probability of, because there's infinity to work with, that explosion out, that same explosion out that results in the current universe and reality we live in, has happened an infinite amount of times before, and will happen an infinite amount of times in the future. Does that make sense? Did I explain that?
It does make sense. It does make sense. So, okay, so you're asking the probability that the process has kind of been ongoing will continue to be ongoing.
Yeah, and that at a certain point it just replicates.
It's a really good question. It's a really good question. It's interesting that you phrase it as the probability of that being an option, as the kind of rubber band thing being an option, because our ideas about the fate, the final fate of the universe, are all kind of based on the curvature, analyzing the curvature of the universe, and there's a lot of math that kind of goes into this, but there's a critical density that take that with the curvature, and it tells you something about what's going to happen in the end. So at the moment, with our best guess, we think that the universe has a flat curvature. But okay, I'll take this opportunity to explain a little bit about dark energy and also dark matter. So you mentioned a little bit earlier about not knowing, maybe even 1% of what's really out there, and I think that's fair, because dark matter is literally most of what's out there, but we can't see it and don't know what it is. So that's why we call it dark. The way that we know it's there, though, or I guess one of the ways that we know that it's there, there's a few ways, but one way is looking at rotation curves from galaxies. And I promise this will get back to your point soon.
No, this is good.
Looking at rotation curves from galaxies, we know what using our kind of like, classic gravity model and the light that we can see from the matter that we can see, baryonic matter, that's the name for the matter that we can see. We know from looking at that what the velocity curve should look like as you get away from the center of the galaxy. Like, we know that things should like slow down as you get farther away, because I mentioned earlier, like, gravity is proportional to the inverse of like the square of the distance. The farther away something is, the lower like the gravitational force. So things should slow down as you get out, as the forces are, the forces involved are weaker. But they kind of don't. They don't slow down the way that we think that they should. So we know that there's more mass there than we can see with like our eyes and with our telescopes. We know that there's something, but it's dark. So that's dark matter. And that's literally most of what's out there. And we have no idea what it really is, which is kind of hilarious. So then the other dark is dark energy. Now, dark matter and dark energy aren't exactly related. We just call them dark because, like, that's our way of saying we don't know much about them. Dark energy, we know of its existence from measuring. You always hear this thing about, like, the universe is expanding, right? Well, here's what that kind of actually means. What we can do is we can measure for faraway galaxies. We can take their distance, measure their distance. We have a few interesting methods of doing that. With telescopes, we measure their distance, and then you can measure from the light that you get from them how shifted that light is in, like, we call it red shifted. It's shifted in like the lower energy direction, like the lower frequency, longer wavelength direction, because it's going away. That's why. So we measure the shift, the red shift, and that tells us how fast the galaxy is moving away from us, right? So if you plot the distance versus that recessional velocity, you get a nice, pretty line, and the slope of that line is called the Hubble constant, which basically just tells us some stuff about how quickly. It tells us, first off, like, the age of the universe. You can get an estimate. We got about like 14 billion years from that nice, pretty line, and it also just tells us generally, like, look, the farther away something is, the faster it is receding. So that's what we mean when we're talking about the universe is expanding. And there's a couple other ways that we know that the universe is expanding. And dark energy basically is responsible for speeding up that expansion. That's what that is. That's really all that is. Dark energy is responsible for speeding up the expansion of the universe. We know that the expansion is accelerating, and we don't super duper know why. But right now, we're just calling whatever it is that's making that happen, we're calling it dark energy. And so now, to get back to your original question about, like, fate of the universe, the reason why it's so hard to answer that question about, like, the probability of the rubber band versus the big crunch versus, like, the perpetual expansion versus the, like expand and then just stop and that's it. The reason why it's so hard to answer that question is because our cosmological models are so dependent on knowing densities and on knowing, like, relative proportions of, like, radiation versus, like, baryonic matter versus, like, dark matter and dark energy, like, and the fact that we don't know that much about dark matter and dark energy makes it really hard to have a ton of faith in our models. But like I said, right now we have the relative proportions that we think are true, and we have, like, the flat curvature that we think is true. But until we learn some more about dark energy and dark matter and, like, why the expansion of the universe is accelerating, it's really hard to actually say what the end is going to be. And there's a lot of cosmologists working on this. Cosmology has always been, I always felt like it was, like, way above my pay grade because I do, like, galaxy evolution. Like, I keep it, like, a little smaller. The stuff that cosmologists do makes my head spin, and I feel like I could not do that all day long.
Well, I'd imagine both disciplines, like, feed into each other.
Right.
So maybe that's one question. My initial question was going to be, like, so what does the roadmap look like? Like, what are scientists doing to further their understanding? Like, what kind of tests are you running? And then what does the cross-pollination look like between disciplines in astro?
Right. Okay, so that's a really, really cool question. That's a great question. So I guess I could talk a little bit about how we kind of look into dark matter, which is like the first part of your question. So in large cosmological simulations, there's a pretty well-known one called Illustris that a lot of people use, and it's just like a big simulation. You can see, I mean, it literally just puts stuff in, and it pops out like a little universe or whatever, and it's really cool because you can see kind of like where baryonic matter, the matter that we can see, remember, baryonic matter, like where it kind of clumps, where it's concentrated, galaxy clusters, which are places where like there's an obvious concentration. And so our idea about that is that those are areas of concentrated dark matter that like subsequently attract baryonic matter. So where we see big clumps of matter that we can see, there's probably also clumps of dark matter that we can't see that are kind of like the seeds for that kind of like accretion and structure. And we talk a lot about like filaments, where when you look at these simulations and you look at the large scale structure, whenever an astronomer says large scale structure, that's what they mean. Like they can see like the filaments, like where baryonic matter is like sort of concentrating itself, and that's where like the dark matter must be. Like, according to just like gravity, right? Like there's got to be more mass there that we can't see. And so that's one way that we kind of dig into dark matter, is by looking at simulations, looking at this kind of large scale structure and mapping out where clusters are, basically mapping out the concentration of light that we can see to get a sense of where is the matter that we can't see. And so now to answer the second part of your question about how that involves interplay between areas of astrophysics. So like galaxy people, right, we're going to look at dark matter halos associated with our galaxy. So when I say halo, I really just mean kind of like so there's two kinds of halos. There's like a halo as in structurally in a galaxy, there's a halo, meaning like think about the Milky Way, the structure, everything has a name. So there's like the bulge, which is the big kind of ball of stars in the middle, and there's disk, which is a flat plane kind of surrounding the bulge, and then all of this stuff is the halo. That's stellar halo. Well, there's another kind of halo that's a dark matter halo. So that's like the surrounding kind of circumgalactic area, but it's all the mass that we can't see, right? So there's the halo that we see, there's a halo that we don't. And so galaxy people look into, again, these same kind of like distributions to get a glimpse at like the dark matter halo, the halo that we can't see. Gravity tells us a lot about that. Gravity is kind of like our indicator that there's some mass there, whether we can see it or not. So the galaxy people then, in turn, can kind of pass that along to the cosmology people that run these simulations, right? They can say, here's all my observations, here's what I saw from this cluster of galaxies or this one galaxy, here's like distribution of light, distribution of matter. Now, you take that and do some cool stuff in your computer and like show me what that means. And then they run simulations and they try to get ideas of large scale like cosmological structure based on the observations and also the simulations that smaller scale people, galaxy people run. Now, even smaller than galaxy people, there are of course like star people. Like there's lots of people who do stars, people who do exoplanets. So that stuff is foundational as well, because although like, sure, an individual star or a star system or whatever might not tell us super much about large scale cosmological structure, it's still important understanding how stars live out their life cycles, because that tells us something about how galaxies live out their life cycles, which tells us something about how gas and like matter is spat out and taken in and passed around and recycled, which tells us something in turn about, again, like the large scale structure, the interplay between galaxies and galaxy clusters. That tells us something about the large scale structure. And yeah, I mean, that's really it. I mean, the large scale structure refers to, again, that which we can see and refers to that which we can't. And they're both very important.
Yeah, that's fascinating. how sort of all of these, I guess, smaller scale studies filter in its input data for the larger frameworks. But I'm sure that once you have a better understanding of the larger scale, it helps inform how things at the smaller scale are formed. What about the actual flow of information? How do scientists get this data? They're, I guess, fellowships. They read each other's scientific papers. Like, is the
Right.
system optimized for information flow right now?
I think that astronomy is a very special science for this reason.
Hmm.
A lot of astronomical, astrophysical data releases are public. I'm going to name one in particular. In
Hmm.
2016, I did a research project at Texas Christian University, which was great because it was in Fort Worth, and I'm from Dallas, so it was like literally an hour from my
Quick
house. It was
trip.
so convenient. But the data that we used was from a big, like, years long project called the Sloan Digital Sky Survey, SDSS. And we were using data from the fourth, like, iteration, SDSS 4.
Mm.
And the specific data set was called MANGA, because astronomers love acronyms and they try really hard to make them fit, even when they very obviously don't work. You can't tell an astronomer no when it comes to a ridiculous acronym. They're going to find a way. So manga, like, yes, literally like Japanese comic books. So stood for mapping nearby galaxies. That was what it stood for.
Mapping nearby galaxies. Okay, I could see
Yes.
that.
Yeah, they capitalize certain letters to make it optimal. Yeah. Anyway, so we use the manga data set, and it's very, first off, it's very cool how that data is stored. It's stored in these data cubes. So it's like literally imagine like a normal plot, just like a regular, like you have an x-axis and you have a y-axis, right? And like there's something being measured along one axis, something measured along the other. Well, the data cubes take it one step further, and you've got kind of like a z-axis, you know? You have a length, width, and like a depth. So the depth is like the same, two axes, the same two parameters, but being taken at like a bunch of different places, like on the sky within the galaxy that you're looking at. Because the way it works is like it uses these fiber optic bundles, like IFUs, what they're called, and
Mm.
they're placed into the telescope, and it trains on the galaxy that it's observing at that time. Um, and each fiber trains on like a spot, and it takes the light and it takes like a spectrum, like you distribute the
Wow.
light into its constituent wavelengths, and it takes all this info from each of these little spots, and so you get a whole data cube that corresponds to like, okay, here's this galaxy and here's everything we have on it. These parameters taken in all these places. So to go and get the data, you just run in and you grab it. You say, I want to see the amount of oxygen, or I want to see the amount of sulfur, and then I want to see it, for this galaxy, and I want to see it for this galaxy. You go in and you just grab, you got what you need. It's this really
Mm.
cool format, right? It's packaged brilliantly. Um, yeah, so to speak to your question, all of the data releases for Sloan, like SDSS, they were completely like public. When they released data, anybody could get in there and take what they want, take what they need. And so that's my answer to your question. Is it like astronomy in particular is really optimized for information flow, because a lot of the stuff that we put out is public. Like anybody who wants or needs data from a particular survey, a lot of the time just wait for the release and you can get it. Even if you're not like a professional or whatever, if you're just a real enthusiast, you're an amateur astronomer or whatever, you're really into it and you want to do some stuff in Python, just open it up and have fun, you can. Like, we encourage that. So I think I can't speak too much for other fields, but I know that astronomy is pretty optimized for information flow just because of the nature of what we do. I
Hmm.
mean, think about some of the larger projects, right? Interferometry, that's a big word that you might hear sometimes. It basically just means multiple telescopes being like combined to kind of function as one. So signals from multiple telescopes being put together to get you a bigger picture than you could ever get by itself. That's how we got that the famous EHT, Event Horizon Telescope,
Mm-hmm.
that image that we were all like holding our breath waiting for, that's how we got that, was by combining signals from multiple telescopes, interferometry. That was a like huge, like that's like a worldwide kind of collaboration. You have to have people across the globe talking to each other, working on that together. So by the nature of what we do, we cannot have things closed off. It's just not going to work. Astronomy doesn't work if people can't talk across the globe. If I can't ping somebody in Australia and say, hey, what are you finding? Or, hey, can I use your telescope at this point? Let me apply for grant funding to use this telescope way, way over there. Astronomy doesn't work if you can't do that.
Sure.
So yeah, astronomy is pretty optimal for information flow.
So that's good. And maybe this is because I want to leave us some time to also talk about, the importance of identity and inclusivity in the discipline, right? Because it's not just about what structures exist to help facilitate information flow, and it sounds like there's some good ones there, but it's also about bringing more people into the fold and having the confidence and agency in order to contribute effectively to these systems. So, tell me, or tell the audience a little bit more about how your identity shapes your outlook on how you participate.
Yeah, sure thing. So I guess the first part of that then would be kind of enumerating kind of what that means, like what my identity is. So like I'm Black, and I'm cisgender, and I'm male, and I'm gay, and chronically ill. And so in terms of how that affects my, my doing astronomy, I guess in the most practical sense, I can't do science if I'm not functioning in real life. So things about my identity that make it hard to function in real life necessarily make it hard to function in science. So, as a chronically ill person, if I'm having some really terrible, insurance hang up, that's affecting my real life. That's going to affect the science that I do. As a Black person, if, there's another, for example, like another shooting of like an unarmed Black kid on the news, that's going to affect my personal life. That's going to affect my science or my will to do science, or like how much I care about the science that I'm doing in the moment when there's like this much larger thing going on, right? So in the most like bare bones practical sense, you can't separate science from real life. But more than that, I would argue not only can you not separate science from like real life, science at its foundations is like complicit in all of the like real life like racism and sexism, all of that. Science is absolutely complicit in all of that, because some of the earliest justifications for racism were scientific. I mean, you have phrenology, people walking around measuring skulls to prove that white people are the smartest because like their skulls are the biggest, when there's no scientific basis for that. And of course you have things like, medicine, of course, is like rife with instances of racism in the past and still today, like forced sterilizations. And of course, like right now, like literally 2019, Black women have higher maternal mortality rates than everybody else. So science is, you can't separate it from your life because it is absolutely complicit in all of the atrocities and negativity of real life. And that is why it's so important to change the picture of who does science and who can be a scientist. Because when you open up your textbook and you just see like white man after white man after white man after white man, it begins to say something about whether you can actually do it or not. And that's why it's important to show other people, to assure like kids and teens coming up that like, okay, I know what it looks like, but don't worry about that. You can do it. You absolutely can do it. And I've talked about this before a little bit. Astronomy is kind of uniquely positioned to be more sensitive about the need for inclusion and for like changing narratives and for making a less white, less male, less straight, less cis, picture of science. Because astronomy is a very kind of human thing. It's at the heart of it, it's us getting to know the universe around us, which speaks to our humanity. It's something that we want as people. It's something we want as a species. And I think that uniquely positions astronomy to be sensitive to those kinds of issues. So that's why you'll see astronomy in a lot of ways is kind of ahead of some other fields, especially like just like physics, like pure physics. Astronomy is often a little bit ahead in terms of thinking about these kinds of issues, working on these kinds of issues, making progress towards fixing these issues. But my caveat there is that we're not perfect. And one huge example that is dominating the media right now of how astronomers have a lot of work to do is at Mauna Kea. The 30-meter telescope is kind of slated to be built when there's already like 13 telescopes on top of that mountain in Hawaii. And so indigenous Hawaiians, native Hawaiians are like, hey, could you maybe not build this telescope right here? There's so many for you to use, and we'd really rather not. It's a sacred site. It's a sacred site, and we'd rather not have it desecrated by the building of yet another telescope. And of course, there's like more of like there's a legal argument about how they obtained the permits, and like that's all one thing. But there's just the very base argument of, what right do you have to come onto land that is stolen? Hawaii was stolen. It was a kingdom. We took it literally. So what right do you have to come onto land that is literally stolen, and then drive up to the mountaintop with your construction crews and ignore all the protesters that don't want it? Yeah, literally. Who are you to ignore native Hawaiians on Hawaiian land? That's like totally against notions of indigenous sovereignty that should be in place. And a lot of astronomers are, on the side of the indigenous Hawaiians. Like, yes, absolutely, this is your land, it's a sacred site for you. Space is always going to be there. There is not really a rush. I mean, this stuff has been around for 14 billion years. There's no rush. We don't have to build this right now, and we don't have to build it right there. There's other ways to look at space. There's other places to make telescopes. There's an alternate site in the Canary Islands for this thing to be built. We don't have to do this. What will not always be there is that culture in this time. What will not always be there is that mountain looking exactly the way that it does. So why would you prioritize something that there is no real time limit on over people that are living right now? That doesn't make sense. And of course, it's a colonial question too. It's a colonial question of who are you to come in and say that you know what is best for the indigenous community? That is so colonial for you to step in and say, oh, well, this will be better for you because X, Y, Z. This will be necessary because X, Y, Z. This will do so much for the island and so much for revenue. None of that matters coming from somebody who's not indigenous. None of that matters coming from somebody who's not had their autonomy taken away by the United States. No, none of that matters coming from somebody who doesn't know what it feels like to be colonized. None of that matters, And just as I said, a lot of astronomers are on the side of indigenous Hawaiians. A lot of astronomers are showing their true selves and saying these very, white savior things like it'll be better for you, the community needs it, or even referring to these really terrible, hack job surveys that are we interview 75 Hawaiians, not even necessarily indigenous Hawaiians, just people who were born in Hawaii, which they could literally be white,
Right.
So these terrible surveys, and these are scientists, real scientists who are pointing to very obviously bad data to back up their point. And it's wow, I feel like we're better than this as a field. But that's just an example of how, as much work as we are doing in the right direction, we are not perfect, and we have a lot of work left to do.
Yeah, right. This, everything that you said, very well put, very eloquent, and I agree. And I think one of the things that's heartening to see around Mauna Kea, and also even on Twitter, there seems to be a lot of solidarity and support amongst, I guess, the young millennial astronomy community. And that's really great, right? Because it's not just you being socially progressive, but you're also the scientists that are publishing these new discoveries.
Right.
And that feeds into itself. It's like, on the one hand, like if you have in the court of public opinion, what gives you credibility are these scientific discoveries. And then also, if you're setting best practices for not just how to treat each other and being more inclusive, but also to treat people with respect. I would hope that the ultimate result is a better society and a better world. And another thing Moy and I discussed, it's like, all right, so yes, that is, to me, uh, also appears totally colonial practice. Like, we're setting, somehow our scientific cultural imperative outweighs the history and culture of the indigenous population. That's not right. But look 1,000
Mm-hmm.
years into the future. Like, what happens, or I don't know, 50 years or 100 years, when we start colonizing or expanding into the solar system? Like, if we set bad practices now in astro, like yeah, I mean, I get what you're saying. I don't think I can say it better than what you said, but we need to set ethical best practices now and respect the cultures that exist today, at the
That's
risk of,
real. And
I mean, wiping out humanity, honestly.
yes, and the good news about that is that we do have people thinking about that. A friend of mine, Dr. Lucianne Walkowicz, a few years ago, she was serving as the Library of Congress chair of astrobiology, and her whole thing was like Mars ethics, right? She was like
Mm,
her focus was like being a Mars ethicist, and that's exactly the kind of thing she was thinking about. Was like, when we say colonize Mars, why are we choosing that word when we know what that word did for us here on
mm,
Earth? Is that really the narrative we want to push? She did lots
right.
of thinking about that. Um, and she's amazing. She's like ridiculously cool.
Mm-hmm.
But yeah, we do have people thinking about that kind of thing, which is good. And I just hope, I really hope that the astronomy community at large, I hope that we all see why it's necessary to have people thinking about those kinds of things, because it's the double-edged sword with like growing social consciousness is that it becomes kind of, unpopular or like out of vogue to speak against that growing consciousness. So if people have very like antiquated, narrow-minded ideas, whereas at one point they might have felt like empowered to come out and say them, so we would kind of know what we're working with. Nowadays, it's almost like they kind of want to hide it because generally astronomy is going in a progressive direction. So it's
Right.
harder to know. It's harder to know what we're up against because people don't want to come out and like say it. You know what I mean?
You bring up a great point, and I don't think it's just the case in astronomy. It's like, you want the right ideas to win, but you want there to be clash, because the way that people get educated is by seeing these ideas clash, and the better, hopefully more ethical ideas win out.
Right.
So
Right.
yeah, I mean, I think that's we should strive for that. It'd be interesting to see, like, when you open your planetarium, like, is there going to be? I mean, you're going to be fighting against that, but is there, like, what are some? It would be interesting to think about, what are some ways to promote like intellectual and healthy debate without
Right.
empowering the evil ideas, but at the same time demonstrating how the ethical and good ideas win out against, something that's racist or
Right.
colonial, or yeah. And hopefully, one of the things that I'd like to accomplish with the Astrolennial series is getting that perspective out, exposing it to a lot of people that might not otherwise hear it from a scientist like
Right.
yourself. So I think that's also important. Another thing I wanted to mention is, I saw this on your Twitter feed, and I briefly looked into this, is one of, I guess, somebody from the Astro community recently passed, Jose Flores Velasquez.
Yes.
And it's been really amazing to see the outpouring of support for somebody in the community.
Mhm.
And there's, we don't have to talk about the death specifically, but there is a GoFundMe,
Yes.
and people can find the link on your Twitter account. And
Yes. On my Twitter, I'll give it to you. My
yeah,
Twitter is at KeShawn Rants. That's my name, KeShawnRants. You can find, I retweeted a bunch of things about Jose. You can find link to his GoFundMe, the link to his friend Alfredo, who was also murdered in that shooting. You can find link to his GoFundMe as well. And yeah, I mean, again, I'm not gonna like go too much into it because it's rough and fresh, but we lost somebody really fantastic. We really did, and in the most senseless way. Yeah, and all I'm gonna say about it is that it reminds me that it's very important to. I keep saying the people that you love. It's important to love them out loud, and it's important that they know how you feel about them, because you literally just never know. But with the climate that we've got, particularly in the U.S., with the way that we think about guns, the way that we handle guns, the way that we think about violence, you just never know. And yeah, just that's all. Just the people that you love, like make sure that they know.
That's a great point. So maybe let's wrap things up and remind people that you also have a SoundCloud account and you have a lot of beautiful covers there. Maybe share with people how to find you on SoundCloud and tell us what's the next song that you're thinking about covering.
Sure thing. So my SoundCloud, you can find the link in the bio on my Twitter, which I just gave you, but also it's soundcloud.com/KeShawn-Ivory, my name. So I have a few things there. Every so often I'll go through and I'll like listen to everything on there and I'll be like, that is trash, and just delete it. Or I'll be like, oh, that's all right, but I should probably like do it again because you just get the feeling you could do it better the second time. But yeah, I have a few things there that I curate very heavily. The last thing I did pretty recently, I covered the song "I Don't Smoke" by Mitski, who's an artist that I adore. I saw her live. The next thing that I want to cover, I really love the 1975. Like recently, they're like becoming like my favorite band, and which is exciting because they have a new album coming like soon enough. And so there's a song from their last album called "Be My Mistake," and it's just a pretty straightforward, like almost like guitar ballad. And I like doing acapella covers of things because that's kind of what I did in college. And so I'm thinking probably want to do an acapella of that song. I think that'd be fun.
Nice. Cool. Well, KeShawn, thanks so much for your time and your perspective. If you have any parting words, anything you'd like to say.
Parting words.
Yeah.
Sure
anything
thing.
we didn't cover.
Yeah. Well, okay. So one, I'm gonna say like long term, everybody keep your eyes peeled for the people of color planetarium. We have a name. We have a name for it, but I'm not gonna reveal it yet. So
Okay.
that's hush hush. That's a long term thing. And also, yeah, just if you follow my Twitter, pretty soon I'll get like a proper research project because I am a grad student. So pretty soon I'll get to talk to you all about like what I'm actually doing as far as research. It'll be fun. Post cool threads about the space stuff that I'm doing. And if you want to know more about my graduate program, it's a pretty cool program. It's the Fisk-Vanderbilt Bridge Program. It's really unique and it's really special.
Oh yeah, let's talk about that for a couple of minutes because I think it's pretty important.
Okay, cool. So Fisk-Vanderbilt Bridge. So the bridge refers to like it's a master's to PhD bridge. So I'm in the master's phase right now, right? So I'm a master's student at Fisk University, which is a historically Black university here in Nashville. But a lot of my coursework and all of my research happens where I am physically right now at Vanderbilt, because they have like more of like the astro stuff. So right now I take a physics class over at Fisk, and then I take a bunch of astro classes and do research here at Vandy. So the really special thing about this program, there's a number of special things, but I love the fact that I attend a historically Black university, small, like liberal arts. So like the pedagogy, like the teaching, it feels so personal and it feels so small. And of course, there's like a great history, right? Like W.E.B. Du Bois went to Fisk, which is like amazing to like walk around where he was literally a student. But at the same time, I get all the resources and all the kind of like scientific advantages of like a big private school like Vandy, right? Where I get to come over here and take astro classes and do research with like, top of the line, everything all the time. So it's really like a best of both worlds kind of thing. My friends refer to it as like a chicken dinner with a side of quinoa is how they describe it. Fish with a side of Vandy, but it's very special. It feels like I'm getting the best of everything. And then the idea is that after the master's phase, I'll have applied to PhD programs, and then I can successfully bridge over into a PhD, either here at Vandy or wherever else I get into and decide I want to go. But yeah, that's the idea. You come in, you're a master's student, and then they help you bridge into the PhD step. So I really appreciate the program because they look for unconventional metrics
Hmm.
to mark who to accept. I think that one thing a lot of grad programs get wrong is they put a lot of stock and a lot of value into metrics that ultimately don't tell you anything about people, like test scores and even grades to a certain extent. You know, there are times when that doesn't tell you the whole picture. And the Fisk-Vanderbilt Bridge puts a lot of effort into looking for those alternate metrics, looking to those other ways of determining how you be successful, how you handle hardship. You know, sort of grit is a big buzzword, but they actually look at grit and perseverance. So I'm grateful for them seeing the value in my experience in my application. I'm grateful for the experience of going to an HBCU, and I'm grateful for the experience of having access to Vanderbilt resources. So if anybody wants to know more about bridge programs, because this is not the only one, there's others with kind of the same goal of increasing equity, access, representation, diversity. So if there's others that you want to know about, literally DM me on Twitter. DM is open. I'm responsive. Just talk to me.
Cool. Well, thanks so much, KeShawn, and best of luck, and I'm sure we'll talk soon.
Yeah, thank you so much for your time.
All right, take care. Bye-bye.
See ya.